So now let me go back to the contact bodies presentation where we looked at two spheres. And what we're studying here with the two spheres is you have two spheres coming together in contact. And I also discussed how you can calculate the contact area, which is given by the radius provided here, and depends on the force applied to these spheres, and depends on the modulus of the materials involved in the Poisson ratios and the radii of the spheres. We also discussed how the maximum pressure can be calculated due to these these contacting bodies. We also discussed that you can determine the indentation or how much deflections you have from these two spheres coming together based on the formula here at the bottom right. And finally, we then discussed that the principal stresses can be calculated using strength theory of elasticity. You can calculate principal stresses, and you can calculate all of them, sigma 1, sigma 2, and sigma 3. In addition to that, you can calculate max shear stress. So now what I want to do is plot for you the von Mises stress as you go through Z. And what I'm trying to do here is start here at the surface of the sphere and then move deep into the material to see what's going on. And when we do that, what you see here is in the y-axis, what I'm plotting here is a ratio of stress to the maximum pressure. That's the y-axis. In the x-axis, in the z-axis, what you see is the depth of where I'm looking at the value of stress. So for example, here you see it in terms of A. Well, because here what we're doing is we're using A as a radii. And so what we're doing is that contacting area with radii A is what I'm using as a measurement as I go deeper into the material to look at what's going on. So Z is a depth, but it's in terms of A. And then the ratio of stress is normalized to the maximum pressure. So what you notice here is that the max shear stress reaches a peak value about half A, and the von Mises stress also reaches a peak value here at the very top. You can see here. So the high stress is not occurring on the surface, rather is occurring just below the surface. And because of that, you actually see pitting in a lot of situations where you get spalling and pitting, where you can get materials coming apart at that surface. And that's occurring because the highest stress is occurring deeper into the material. You can also then study other cases. The other cases can be derived. So the other cases I want to study all can be derived from the equations I'm presenting here. And the equations I'm presenting there are in terms of radii. So what if I want to study a sphere that's on a flat plate? What if I want to study a sphere on a groove, for example, a spherical groove as what you see here on the right-hand side? Well, you can study that. And what you will do then is adjust the radii of one of them you'll substitute the radii of one of them to be infinite. Because if you do that, then you get a flat plate. So you can actually use the same formula I provided earlier and choose R in such a way that it gives you different situations. On the right-hand side, if I choose the radii to be negative in value, then I invert the curvature so that now it looks like a groove rather than a sphere. With that, so let me study the first case first. The first case is sphere on a flat plate. So R2 here is infinity. So what I'm going to do is plug in R2 to be infinity here. And if I do that, then I assume the Poisson ratios are the effects are negligible, because you see here the Poisson ratio of metal is typically 0.3. 0.3 squared is going to give you 0.09 anyway, so it's going to be in the noise. 0.9. If you consider that 0.09, if you consider that 1 minus 0.09 gives you 0.91. So you can use that number. And if you use those number, you get that the contact radii is 0.88, the force applied, R is the radius of the sphere, and E is the modulus of this material. In this case, I assume that the two materials have the same modulus. I could have assumed that the two modulus, different modulus. But in this example problem, I'm assuming the two have the same modulus and giving you what that looks like. But you should be prepared to use any of the formulas I showed you earlier, and you can actually do it very quickly. The pressure that you get in this case is also provided here for modulus that are equal in Poisson ratios. And then the amount of deflection you get from that sphere indenting into the flat plate will be provided here as well. With that, I want to see if there's any questions. So we'll go into the case of a sphere on a groove of material. So I'm looking here at a sphere that's sitting on a groove. And in this case, what you see here is I can take the radius of the second material and make a negative value. By making a negative value, what I did, I inverted that sphere. So now it looks like a groove. And by doing so, I can actually analyze it using the very same formulas I discussed right here. These come from here, basically, pretty much. They all come from here. I specialized it for the case of the modulus being the same. So that's the difference here. We made the modulus the same. They don't have to be the same, but I did it so that we can study that one case. And when you do things, simplify quite nicely, where the contact radii is provided by this equation, and then the pressure is provided by this equation, and the deflection is provided by this equation. So I invite you to check it out, to try the calculation yourself, so you can see that the equations that are provided here, right here, which is the most general equation, two spheres come into contact, simplify for the case of the flat plate. For the case of the inverted or the groove, this case and this case can be simplified to these equations. If the modulus are the same, you will get this. So I invite you to try that, and I think you will be happy to see that you will get that. So any questions on this topic before I move to the next topic?